I work on the real-time platform at AppNexus. Real-time, because if you look at constraints that are real-time, it's more like online. And what we see is AppNexus grew very quickly in the past 6 or 7 years. And we're definitely not like Google scale, Netflix, or Amazon. But it's very interesting. We're now running the systems I'm going to talk about on about 3,000 machines. And we can definitely see how we started with 10 or 20 machines and just organically grew and made a lot of mistakes. And now we're trying to fix them. So this is what I'm going to talk about, how we kind of made mistakes as we grew, and now we're trying to fix, and what the fixes look like. So I don't know if you read the bio before working at AppNexus. What I was doing was a PhD in operations research. Really, what I was doing was playing with the runtime system for dynamic languages. And then at some point, I had to graduate, and I wrote a thesis. So after writing my thesis, I went straight to AppNexus, and I figured I'm going to just write standard C. It's going to be great. No more doodling around with crazy runtime system tricks. And a year and a half later, I woke up, and I realized I made a grave mistake. For some reason, I started from something that's fairly close to normal C and was now very similar to what you would get from a dynamic or safe language runtime system. I thought about what happened for a while, and then I realized I think it's a good thing, because as you scale a system, you can either take a dynamic runtime system, so you start working with a JVM, and then you get so much data you have to start doing your own memory management on the side, or you can start with C and slowly add more JVM-like features. It's not clear which is better. I think for us, it works better to start with C just because that's what we had when we began. If I were to do it from scratch, I don't know. So once upon a time, very many years ago, Brian O'Kelly decided to write its own add exchange code. Then it became its own add bidding code. And the data sets were so small, it was very nice. We could just run one process per core. It was shared nothing. And the overall architecture was pretty good. It was a clean RPC layer to separate everything with mostly standard HTTP and JSON. And then growth happened, and we were running out of RAM. So what do you do when you have a system with 8 cores per server? And now if growth continues as it is for 3 to 6 more months, you can only run your code on 1 or 2 cores. You're wasting the vast majority of your computing power just because you decided to do shared nothing, 1 process per core. The solution, obviously, is to add threads to the mix. You say, all right, I don't have enough memory to run 1 process per core. I just do 1 process per machine and 1 thread per machine. As we all know, this always goes very well. And yeah, so that is a solution. I don't think it's the right approach if the only reason you're threading is because you need more RAM. There are ways to share memory between processes. We probably should have used that instead. But if you do have very complex communication patterns, then yeah, of course, use threads. If you don't, I would say you probably should avoid that, even if it's so much easier to start with, because there are so many problems that you have to fix as you introduce thread in your system, and then you try to make them work and scale, and realize it's not fun. So we started with threading and just 1 big reader lock. Obviously, this led to latency spikes as everyone was waiting for the big lock. So we went to much finer grained locked. And that led to performance problems, because now you have to acquire and release the lock, and of course, a ton of bugs, because the lock ordering issues and documentation is always lacking in an internal project. So eventually, what we went for is much finer grained locking, but less of it, and focusing mostly on non-blocking algorithms with safe memory reclamation. I think that's a good way to structure your updates if you have something that is very similar to our workload, where the write rate is low. You can restrict the writes to exactly one thread, and most of the work is read-only. But yeah, so this is how we got stuck with a very complex system that few people can work on. So looking back, I think there are a few good decisions that were made. On one component, the safe memory reclamation was based on epoch. So this also forces the application writer to define what is like a transaction or a request, and that gives you an easy way to add in more logic to like stand up and tear down a request. We also use an internal wrapper around malloc, so we could now know what type we're leaking. That's also useful. But also, after the fact, we realized it's a good way to kind of group allocation points and have custom logic per type to say, well, this kind of type, this is the type of special allocation I want to use, otherwise use something else. What else? Oh yeah, HTTP, as we all know, always useful. If you have an internal service, add an HTTP listener, even if it's only to be able to get some stats. You'll save a lot of time where you would have to GDB in prod, which is never good. And finally, there's one that's not sure if it's good or bad. We use Gimli to get backtraces on crashes and then send that via email. The emails themselves were good because they enable kind of ad hoc analyses. You can do clustering with email filters, that sort of thing. The only issue is Gimli is not a good tracer, so it would lie to you. So do use a tracer to get some analysis on your crashes. Don't use a bad one. We are now using backtrace, which is mostly accurate. It's a lot better, and even does the clustering for me, so I don't have to write hacky email rules. Yeah. So we also had an interesting culture at work. Our code base was very fast. It was correct. I think you could show that most of it was fine, like the very complicated part, but it was impossible to work with. Every time you had to make a small business change to be sure that it wasn't, I don't know, either going to crash the machine or leak a lot of memory or break some random invariant in a different module, you had to juggle in your head 4 or 5 things at the same time at different abstractions level. You might have to say, oh, all right, so this is the lock order, and this piece of code is fine because of the x86 memory model, and this other thing is fine because of the way we receive updates from a different application. Obviously, no one can actually do that, but the issue is when you look back at the code, every time that there's a bug, you can point out to a cause and like, well, everyone should have gotten that right. It's only a lock ordering reversion. Or everyone should have gotten that right. It's just standard x86 memory model. How could you forget it? This is why we hired you. But it's not the programmer's fault. It's just because you have to hold so many things at once in your head to make any small change. So, and of course, it also makes hiring so much harder because you have to hire people who are often interested in kernel development to write standard application code. So I think it's very important here when I look back at bugs that happen in prod. Once it gets to prod, you shouldn't blame the person. You should look at either the process, or in our case, I think the issue was mostly the overall ecosystem in which all the programming happened. And that's a big change that I had to do in my thinking. I think it helped grow our code base. Also, I guess with the same macho culture, there was this idea that the code has to be perfect. So we had an architecture that would either work or crash hard because you shouldn't crash. I think looking back, when you move from 10 machines, I guess that's a fine way to look at things. When you have 1,000 or 3,000 machines, it's OK to crash. If one machine crashes, you just lost 0.1% of your capacity. The only thing you want to avoid is, make sure not everything crashes all at once. And just admit that there will be mistakes. So this system should be resilient because it will be imperfect. All right. So that is a kind of interesting, hard to work with code base that we had, I don't know, I want to say up to 1 year to 6 months ago. And that's a goal that I had when I started rewriting a bunch of the internals and trying to make life easier for people who have to ship real features. I wanted to centralize the pain, so whenever there's something that makes development hard, usually there are two ways to think about it. One is to say, well, everyone just has to get this small thing right. And incrementally, like each increment isn't that difficult, but it adds up, and it's just more stuff that you need to keep in mind. So let's say you add one more thing you have to lock. Remembering to acquire a lock is not hard. Remembering to acquire 10 locks in just the right order is hard. So you should centralize that so there's one person or one piece of the code that has all the pain and all the hard parts of acquiring the locks, and that way no one else has to think about it. Also, just because we wanted things to be fast, we had something like 5 different hash tables, 4 implementation of spin locks. It's not worth it. Simplify, try to find a common ground between all your things, and it will be good enough, and that way people don't have to always remember which variant should I be using now. Yeah. We also had something very, I don't know if everyone has that in their system, but I see it a lot in ours. You can see the workloads and separate it in 2 parts. One is it's critical. It must not have mistakes. If something goes wrong, it'll probably crash a system, but it doesn't have to be fast. And there's another one, which is, well, it has to be fast, but it's mostly OK if there's a mistake there, or it shouldn't crash a system if something goes wrong. We have to use that. We have to determine which part of the process is which. Otherwise, you end up with something that tries to be fast and very safe, and that's hard to achieve. And this one is easy also. I guess it's another thing with C. You just use void pointers everywhere. That's how you do generics in C. And you should just get it right because you're a good C programmer. I don't think that's the right way to say it. Just always try to find ways to get the compiler to help you, or use a better language, really. But oh well, that's a conversation for another time. So one of the things we had with centralizing pain was, well, we use normal malloc, would leak all the time, except at a very slow rate. And sometimes allocations would be slow. So the normal way to solve this is to say, well, just pass an explicit pool around, and everyone knows what pool is associated with each request. And if you're in a thread-based model, that's mostly OK. If you use an event-based, we use libevent, and you have to mutex, demux a bunch of events and a bunch of logical threads on the same thread. Not so easy. It's easy to make a mistake there, and then everything goes wrong as you have use after free issues. So instead, what we did was centralize the pain with an interesting system that uses time to determine when a pool is definitely OK to free and reuse. That took a while to write and convert a lot of code. But once it's done, most application writers don't have to think about it. They use normal malloc. It's exactly the same interface, and it avoids a bunch of leaks under the covers. I don't know if this is interesting as to how it works. What we do is we only use fixed size allocation pools. Each thread has a list of the current pools. We always allocate in the one we created last, and we create new pools on demand. And what we do is we have each transaction. So let's say an HTTP request comes in. You're going to need to allocate some memory. We find the pool that is at the head of the list when it is created. And as long as that transaction is alive, that pool cannot be freed. And also, nothing newer than that pool can be freed. So in a way, when we try to free memory, we look through the current in-flight transactions, and we figure out the oldest one. Any pool that's older than that, then it's free to reuse. That's also very specific to the way our requests work. They are very short-lived. Think if something goes If we have an auction that lasts for more than a second, it's useless, and we should have sent like a default image or a default ad instead of waiting for perhaps a bid that no one will see and no one will transact on. Of course, in the general case, this doesn't work, but it's essential. Just try to figure out what's special about your application, and that will make your life much easier. We're not writing academic papers. We don't try to have the end-all be-all. We're just trying to make our own thing better. So in a way, PHP memory management, just use pools, and at some point that memory will be freed. Save my mail agent. There was a period of time during, I want to say like 3 months, where we had this very slow leak, but every box was leaking at exactly the same rate. We couldn't find why. What we did know, though, is that if we restarted all the bugs at the same time, they would all crash with out-of-memory condition at the same time, which was really great for Outlook. After we rolled out this thing, I don't think we've had any leaks yet. Do we? No? No new leak. Wow. So another problem that we had is we would constantly check for conditions that were almost always false. Like, am I in debug mode? Am I trying to trace something? And it would actually show up on the profile, or we would spend easily 5% of the time making sure that we're not trying to log debug output when we almost never are. So as I was looking at solutions, one of the things that came up was, well, obviously you should hoist the checks out of inner loops. So if you have a loop that always checks if you're going to debug, you should have 2 loops. And that's not scalable. There's no way that coders will handle that well, and we're telling people to copy and paste code. So instead, we decided to go with cross-modifying code, so that self-modifying code except multi-threaded. In theory, it works. In practice, Intel tells you it may not work with a very small probability. But again, we run on so many machines. If one goes down, whatever, we'll just restart it. You can see very similar code in the Linux kernel. We have a simpler version because, again, we're OK with rare failures. This is also exposed over HTTP, which turns out to be useful for debugging. So this is the kind of thing that programmers can write now and say, I'm going to debug. Instead of having if debugging enabled all the time, the first thing there, make sure that all that block is basically a NOP if we know for sure that debugging is not enabled. So that was about this time last year. We're about to hit the code freeze around Thanksgiving, and we had an issue we could not reproduce in debug. So obviously, what you think is, well, it must be the debugging code. I have to enable something in debugging code that will fix the issue, and then I can figure out what exactly the real problem is. It's just, yeah. So that is what we did. We found the one debug toggle that would fix the issue. We figured out exactly what the problem was, but we're not in code freeze, so we could not release a fix. Instead, I had a cron job that would curl all the machines to enable these debug toggles so that it would stay active even if we restarted the box. It's not my proudest moment, but it did fix prod without having to release a new version. And then there's this very interesting hack, which we call core me maybe. The problem is, if we look at the reason for most of our global outages, it was a new kind of request that came in at a very low rate, but you only need one to crash a machine. So if you have 1,000 machines, you have one request that comes each second, and it crashes a different machine. It doesn't take that long to bring down a whole data center. So you could say, well, everyone should code defensively. I don't think that's a good way to see things, because you always have to bubble up error codes, and your code becomes mostly error handling. Instead, we borrowed something from Visual Basic, and we used a signal handler to try and detect when we're in a read-only transaction. So that would be a kind of workload that is OK if it doesn't work. As long as it doesn't crash the system, we can recover from it. So there's no one-size-fits-all policy here. We had to figure out first what kind of updates are OK to try and recover from, which one are critical, and we would rather have the box crash than try to continue with bad data. We also had to think about, let's say you're trying to test a new code. You want everything to crash because you want as much debug info as you can. And then what happens if this condition isn't rare? At what time do you decide, well, I should probably just stop trying to recover from it and crash? So this is what we came up with. The only time we want to start and try to recover from crashes is when your code is not doing any write to shared memory, and it's not billing money. As long as there's no immediately back-to-back crashes on the same thread, if it's not a test build, and it's only enabled on 80% of machines. So we had a nice logic bug in the first prototype where it would do something like Mongo and crash with a small percentage of the time. But if you think about it, once a box is down, it won't receive new traffic. So it'll be another box that will receive the same amount of traffic, and then it'll go, oh, yeah, it's time to crash randomly now. So if you don't want your whole system to crash and you use that kind of thing, it should be always repeatable. The same set of boxes will crash, the same set won't crash. So a couple months later, I think it was January 2nd, I was out back home in Quebec enjoying my holiday, and we saw a new kind of traffic. And the whole world crashed, except no one noticed it. It was only when I came back to the office, I looked at my emails, and I saw like maybe 100 crash emails. Like, oh, that's weird. They all came at the same time. Why didn't I get more? And then I realized, oh, yeah, that's right. We enabled Visual Basic mode. So I looked at the metrics, and if we didn't have that, we would have been out in 2 data center, fully down 2 days during the holiday, and no one got paged. That gave us much more time to figure out what the issue was and to release a well-understood fix under standard circumstances instead of deploying emergency code when no one's looking, really. And the last one, I guess, that we did is we're now building a single writer software transactional memory. So it turns out that even fine-grained locking is hard to get right if you have to demux a bunch of threads that you call threads at the same time because you use an event base, and you enter and leave the event base all the time. Also, we were spending a lot of time just waiting for locks. So there was one application where we tried this to find exactly the right grain for each lock and to use it right. I think it did work. It took a lot of effort, and it hampered development a lot looking back. So instead, we said, well, let's centralize all this concurrency control and try to expose something that it's almost impossible to get wrong when you only do normal business logic. So these are the trade-offs that we made. We said, well, reads have to be fast. Some inconsistency, man, it happens. It just adds. That is what we do here at AppNexus. And there's only one thread that can ever write. Also, writes are rare, and they can be very slow as long as reads are still fast. And finally, that's my one thing that I always try to get is if you use it wrong, it should just throw an error at you. So the way we do it is basically with a handle, double indirection standard trick for NVCC. The only difference is because we only have 2 versions, we can make sure that most of the time the data you want is actually in line with your object. So this is what usage looks, oh, interesting. This is what usage looks like. Before with locking, you'd have to get a read lock, and then you do your null check, like, oh yeah, don't forget to unlock because that will bring down updates n minutes later. And then you do sprintf. There's a function call there. You have to check, is the function call expecting the segment to be locked or unlocked? Otherwise, you'll get a deadlock. Great, right? And then you're like, oh, OK, good, good. Finally, I can unlock. With this new system, what you do is you have one function that gives you the base data. If you don't use it, you end up trying to access a field that doesn't exist. So there's no way you can make it work. And now you don't have to worry about locking. It's all handled centrally when you open and close the request. And yeah, I guess that's the biggest win for me. This thing stopped people asking me, which lock should I be using now? Do I have all the locks that are required on this code path? You don't even have to think about it. So looking back, I think the real problem here is that we went with threads. If only we didn't go with threads, most of this would be useless. So there was this idea with, we're good coders, go with threads, don't fuck up, and it'll be great, right? I think now the better way to do it would be to go back to a standard Unix solution. So use multiple processes, and you want shared memory, then yes, you should share memory, but it shouldn't be the default. It should be explicit. This piece of data is too big, so we'll share it between many processes. In a way, that's kind of the standard architecture for web applications, except the shared memory is the database, and that's very much too slow for us. However, I think I would still hand roll something in C instead of trying to use something standard like, say, Java. Of course, some of it is just path dependency. We had a large code base in C. It's not a good idea to try to rewrite everything in a different language. But there's also that as you scale up, I feel like nothing really off the shelf will work for you. You always have to find what is special about your workload so that you can exploit it and you have a solution that is usable. Also, it's much easier to build your own solution in C than to try to work besides like a garbage collection language. I did that for a while when I was working on Lisp. It only worked because I had hacked on the garbage collector before. It's not a good way to run a production system, I don't think. It makes your whole thing dependent on a very small set of dev who have to understand both low-level C and a virtual machine that is itself extremely complex, usually bigger than your own app, right? So, yeah, I don't know. Scaling is hard. You're going to have to roll most of it yourself at some point. But I don't think that it's a good idea to try and guess ahead of time and do exactly like Google, because everyone's solution will be different. All right.